Hi, everyone. That works. Good, good. Thanks for showing up. I know it's late. We'll try to be as entertaining as we can. First, we'll have our thick French accent. That's a first. But there will be moving pictures. There will be nice slides, so please pay attention. Thanks. My name is Etienne Whittom. I'm the head of Hibernum Labs at Hibernum Creations. It's a video game development company in Montreal. I'm here today with Patrick Roussel.
Hi, everyone.
System engineer at the CDRIN. It's a digital imagery R&D center in Matane, Quebec. Who would have thought? And here it goes. We have a lot to cover today, so we'll go fast. Please, buffer your questions. We'll answer them at the end of the talk. We'll start with a bit of context. So at Hibernum, why are we doing animated productions with Unity, and how do we do it? A bit of a history. Then we'll jump right ahead with Patrick. We'll start talking about real-time motion capture previs, so motion capture. Then I'll jump back in with offline high-quality rendering. So offline means not real-time, close to real-time though, but higher quality rendering from game assets. Then a quick transition to production tools to wrap it all together, some conclusions, and then your questions. So let's dive in. So a bit of context, Hibernum started 10 years ago. We started by creating cinematics for games. So think Assassin's Creed, Batman games from 2005 to 2009. Then we switched to game development from now on, and now we're creating games on all platforms, so PC, mobile, console. We're using Unity for that. We publish our own games as well, and we became a Unity enterprise partner not too long ago. Here's a few of our latest projects. So you can see, Bruce Lee, a 2D beat 'em up. Daredevil Garage, we developed that for Disney Pixar. We made Saber's Edge. That was a launch title for the Fire Phone. Fruit Ninja, we developed the Connect 2 version on Xbox One. That's your favorite fruit slashing experience. And coming soon, Magic Puzzle Quest. So you know about Magic. We're doing a card game for them on mobile. Exciting. Nope. You can do it. Bad clicker. All right, so that's our team. Hibernum has a dedicated R&D team. We call it Hibernum Labs. It grew from 1 to 14 employees in roughly 18 months. It's mostly programmers. We mostly do tech. It also includes technical artists, UX designers, and so on. So everything you will see today has been either done by Hibernum Labs or in collaboration with the CDRIN. And that's where Patrick will jump in with the real-time mocap previs directly in Unity.
Does it work?
It should work.
Okay. Yeah. Hello, everyone. So my name is Patrick Roussel, and I'm here today to introduce you to this new technology that we developed in the game engine that allow us to do real-time motion capture directly in the editor. So I'm working for the CDRIN. Etienne said talk a little bit about the CDRIN at the beginning, but we are a digital imagery research and development center. We are based in Matane, eastern Quebec. We have been working in collaboration with Hibernum since 3 years now, and we have one of the largest motion capture studios in North America that is dedicated to research. So just for the fun here, who knows about motion capture in general? You can raise your hand. Okay. So the motion capture process consists in taking motion of actors, for example, or object on a stage of motion capture and apply these motion into a game, for example. It's just a simple definition. So at the CDRIN, we have multiple technologies that allows us to do motion capture. The main technology we are using is the Vicon system. We have 72 high-resolution camera. So we can do motion capture with multiple actors at the same time in a very wide range of motion. So we have also developed a custom wireless virtual camera. It allows artistic directors to preview the motion in the game directly on the stage. So we don't have to go at a computer to see the motion in the game. We are also doing facial motion capture. We are using Dynamics YZ video-based facial helmets. And when we want to go outside of the studio, we can bring inertial suits without having to bring all the cameras where we want to do motion capture. So what we are presenting you today, we have been working for a couple of years on this tool. You will see it's very useful for cinematic and game production we are doing. So before getting into deep in technical aspects, I would like to show you a quick demo that shows what we can achieve in real time in Unity. The video you will see, it's a cinematic that we have done with Hibernum on a kid game. You will see it's an actor that has been mocapped, the body and the facial animation. So let's get ready.
Hey, Steve. I just learned how to read blueprints with the Wright brothers. Now we can repair the machine. Okay, first, we need to figure out if the drawing is a plan, an elevation, or a section. A plan is when you're looking down on the object. An elevation is when you see it from the side. A section is when you see the inside of the object. I think the one I found is a section. Now we need to go back to the capsule and see if the blueprint will fit. Hurry up, guys. We have work to do if we want to get back home.
So to do this quick demo, we had an actor on the mocap stage with some mocap suit. We also had a facial helmet. It was a Dynamics YZ helmet. It's a video-based solution. And also in the studio, we also had an artistic director that was driving the virtual camera. So here you can see the rig. We tried to make the virtual camera to look as possible as a real camera, so it's easy for the artistic director to feel the motion in the game. So why we want to do motion capture in real time in Unity? There are several reasons why, but the main reason is that we want faster production. You know, in game industry, it's always the key. You know, when we was doing motion capture earlier in a couple of days before, a couple of years before, it was very hard to get the motion in the game fast. We needed to do the cleanup of the data, and we only get the motion back from the motion capture studio a couple of days or even a couple of weeks after the shoot. So we had a rough preview with the actor on the stage, on the model, but never with all the environment of the game and the physics and everything. So now we can really see what we will achieve in the game very early in the pipeline. So yeah. And it's also safer because we can detect directly on the motion capture stage the issues with the motion capture. For example, if you have a broken head on a bone of the actor, for example, a marker can be moved accidentally during the motion capture session. And if you only see the skeleton, it's hard to see that the head is not placed well. But if you retarget that motion onto an avatar, it's easy to see that the head is flipped up, for example. Also, we can achieve better game visual, of course, because with motion capture, we have more realistic animation, but also because the artistic director can really place the camera where he wants in the game. And yeah, so we can even record this motion and play back the action in the editor, so it's more easier to have better visual in the game. We are also trying to democratize the motion capture because mocap is being known as being very expensive. There are so many technologies that we can use that are cheaper for doing motion capture today. So we are trying to support as many as we can in our plugin, so it's easier to use too. So, and also, when we are doing the motion capture, we can use VR helmets directly on the stage. So it can help the actors to get a better visual and a better feeling of the game. So we have done that a couple of times with an Oculus Rift. The actor was seeing the environment before doing its acting, and it was very better acting during when we are making the shots. So here you can see the main architecture of the plugin we developed. What you need to remember is that we have some systems outside of Unity that we can connect to get the motion capture data. Here in this demo, we have the Dynamics YZ system that is the video-based facial solution. It sends us motion capture facial coefficient over a TCP IP format. And we have a Vicom Blade system that sends us data with a native SDK. So when we develop the plugin, we can see the black box is the DLLs that we import in Unity. So we have developed a common previous API. It's native. And in this API, we have some tools we can use in all of the plugins we are developing to connect to the systems and to deal with motion capture data. So And in green, you have the component that we need to put in the scenes to get the motion capture working in the scene. So the main component is the previs controller. It's the main brain of the plugin. It's where we are doing the recording and the playback of the takes. We can also do the retargeting on this component. And we need to add some component on the objects we want to move in the scene. We can drive facial with blend shapes or with facial rig. And we can make avatar move with an avatar scripts, and we can make also object move with a rigid body scripts. So now I have a video. It's how we can start from scratch from an empty Unity project and get the motion capture working in the scene. So normally, here we will start with an empty project, but normally the most of the time we will start with a project existing with the scenes already ready to work. So here we just remove everything in the scenes just to show you how we can import. We will now import a package that contains all the environment and the player where we want to make move in the scene. We also ask an artist to make a prefabs with all the environment already placed in the scene. So we will just add this prefab to the scene, and then we will be able to. We'll be able to import another package after that. The second package that we will import contains all we need to do the motion capture. So we have all the DLLs of the systems we want to connect to, as well as the script needed to do the motion capture. Next thing to do, we will create an empty game object in the scene. It will be our previs controller. It's the main brain of the plugin. We will call this object previs. After that, we will just add the previs controller script on the object. And we will also add some script for each of the systems we want to connect to. In this case, we have two systems we want to connect, the Dynamics YZ motion capture for facial animation and the Vicon system for the skeletons and objects animation. We also need to set up the plugins to connect to the good IP address and ports on the network. And for the Dynamics YZ system, since we can have multiple actors on the stage with small computer that is processing the facial animation on the stage, we need to add a connection for each of the actors we want to connect to. Here we only add one actor in this use case. After that, we will go into our main character in the scene, which name is Marty. We will add a previous avatar script as well as a previous facial rig onto him because we want him to move the facial and the body. On the camera in the scene, we will add a previous rigid body script since we want the virtual camera on the stage to drive the camera in the editor. After that, we can just hit play and do the retargeting onto our previous controller. We will see that automatically when we hit play, the Unity will connect to the systems, and we will see the incoming actors and objects here that we can retarget. And there we get the motion capture ready in the scene. So it's very easy to use, and it goes very fast. And we try to make the plugin architecture the most flexible as possible so we can integrate new systems easily. By now, we are supporting 4 systems. We have the Vicon system and the OptiTrack systems, which are the 2 most used in the motion capture industry. These 2 technologies can send us skeletons and rigid bodies. You just need to know here a rigid body is not the same thing as the rigid body we know in Unity. A rigid body in motion capture is an object that we want to mocap to make an object move in the scene, for example. For the facial animation, we have the Dynamics YZ system that we can support. It can send us some blend shapes or bones animation. And I was also talking about democratizing the motion capture earlier, so it's why we have chosen to implement the Kinect 2 plugin in our tool. For example, with Hibernum Creations, before getting onto the big motion capture stage, they can use the Kinect plugin directly in their studio to prepare the motion capture sessions. Here you can see some features of the API that we developed. We have automatic retargeting to humanoid avatar, so we automatically detect the topology of the bones of the actors that are coming in from the motion capture, the skeletons, and we can automatically retarget that to the avatar bones in the scene without having to do anything manually. It's all automated. We can also record and play back the motion capture data directly in the editor, so it's easy to see the takes we have done. And we can even export to standard formats in Unity, such as BVH, FBX, and ImFile. So regardless of the systems we are using, we can have 4 different systems we are doing motion capture with. And when we export the animation, everything is synced up in one unique file. And we can use that in another software than Unity to do the cleanup of the data, for example. Also, we have tried to make the editor extension the most user-friendly as possible, so we can get up and running in a few seconds. As you saw in the previous video, it goes very fast to set up the editor. And finally, we have chose to implement native core because we wanted more performance in the plugins, and we can even port to other platforms if needed. We haven't done that yet, but if we need to, we'll be able to do it in the future. So where we are going with that, by now we are supporting a couple of systems. We want to support even more systems, and we are doing facial and body animation with multiple actors, but we would like to do full performance capture in Unity. So it's why we would like to implement 2 ends plugin. We would like to implement, for example, inertial system. And that's about it for the animation systems that we develop. Now that we saw how we can animate things in Unity and even record the animation, we'll see with Etienne how we can render these animations to get even better visual in our games.
Thanks, Patrick. So now that we have all this content, we would really like to render it and make the best images possible from that and get this product out the door. So we thought, if we have time, what can we do? So we went back to basics. We said, we don't want to change anything in the project. Let's do the accumulation buffer technique. It's a really old technique. It's 25 years old. It's super simple to implement. You just sample the aperture, move the camera slightly, set its projection matrix, render the entire scene, and accumulate this result in a higher precision render target. Relatively simple. Just repeat as needed, and you get nicer images. I'll give you a quick demo of how it looks, just in comparison to the vanilla solution from either Unity or whatever you write. So here, hopefully, yeah. So we support quite a few effects. We support transparency with depth of field. So since it's not a depth-based effect, it works. The bokeh shapes just naturally appear because you end up tracing them with the accumulation buffer. We support custom, aperture, size and shape, different tints, no problem. Here you see transparency plus elliptical aperture support, which is always nice to have. The same algorithm can be extended to support motion blur. So it's the exact same technique, we just accumulate over time. So you see much smoother results by just accumulating frames within the exposure time of your virtual camera. So we support very fast-moving objects and still yields interesting results, fully customizable, shutter speed from your camera. Since it's a full, it's an image effect essentially. Everything will just work out of the box. So you'll get nice motion blur, you'll get nice duff from the images themselves. So what does it mean? It has a few advantages for us. Well, first off, you can think, it gives you great anti-aliasing right off the bat. It's MSAA with a little bit of jitter, so it gives you great anti-aliasing, even if you don't do, duff or motion blur. It gives you true depth of field. It works with anything that you can, put in a scene. It's very close to distributed ray tracing in that way. The exact same algorithm can be extended to support soft shadows by sampling, basically accumulating light maps and creating soft light maps from that. It's image-based, so you can use forward rendering path, deferred rendering path. You can use anything. It will work as well. The key, the key thing to remember here is that this technique, you don't need to change anything in your projects. If you have an existing in-game cinematic, you just flip a switch, add a camera component to it, start recording your frames, and it will work. You don't need to change anything. So it just works. But there's a catch. There's no such thing as a free lunch. Some scenes, depending on what you render, they will require a lot of passes. A quick example here. Let's say you realize that you need 400 passes for your duff effect, but you also have a lot of motion blur. So for each frame, for each final frame, you need to accumulate 60 samples over time within your shutter, your exposure time. You multiply these, you get 24,000 passes for a single frame. That's a lot of frames. At 60 hertz, it's 6 minutes, give or take. So you end up taking a lot of time to render a single frame. What can we do about this? Well, it's still not a showstopper in some cases. If you have very simple scenes, I mean, we do a lot of mobile projects. Running these cinematics that were intended for mobile on a high-end development PC, you end up having, if you turn off VSync, 1,000 FPS. So 24,000 passes, well, that's 24 seconds per frame. It's not that bad, so we can still use it. If you have large depth of field, so translate to maybe smaller bokeh shapes, so you don't need to trace that much, you need less passes for these shots. If you have short exposure time or there's not a whole lot of movement in your shots, the number of passes you need to get nicer motion blur actually go down. So there's a few conditions. But at the end of the day, if someone comes to you at the very end of your project and I'd like to have this cinematic in 4K, no aliasing, super HD with nice duff and motion blur, that's an option. You can just flip a switch, add this component, and it works. So that's something that worked for us. Here's a quick demo of something we used in the production last year with only the duff effect. So that was what we had for the depth-based duff in Unity 4. So now we just enabled the exact same scene, exact same assets, no changes to get this kind of smooth, creamy result. So much nicer frames, much nicer end product, and we didn't have to change anything. It was just code-based. So we get a nicer result. Quick side-by-side comparison. And that's pretty much it. Looks very angry. All right. Now we thought, let's step it up a notch. Accumulation buffer is nice, but you can't render everything with this. You can't get reflections, refractions, caustics. You can get, most of the light transport you don't get if you just flip a switch. So we said, could we do, progressive global illumination by, implementing a new renderer in Unity? Why not? It's an R&D team. We can do whatever we want. So that's one sample of what we got. That's one scene. To add a renderer in Unity, there's a few challenges there. But first, we won't write a renderer ourselves. So we thought, which renderer do we want to use? So we thought about this. At the end of the day, we just picked Iray from NVIDIA. Actually, we took the Iray Plus plugin from Lightworks. Why did we do this? We used this plugin, we used this renderer, because it's an unbiased path tracer. It will converge to a physically plausible, physically accurate result over time, and we wanted that to generate, reference images. So even if this solution didn't work, we could at least have reference images to use to get other lighting techniques a baseline. We knew we wanted an interactive renderer, so we could integrate it straight in the Unity editor and have real-time progress. We were fairly confident that NVIDIA would upgrade this solution with the latest hardware. And it turns out that we only use, or almost only use, NVIDIA products at the office. It's a game development rig. It's a fairly high-end graphics card that we have on all of our machines. The solution at the time already scaled as we had added more hardware, so we can throw 4 GPUs in parallel on a single machine. We'll give you slightly faster, close to 4x faster render time. And you could also distribute your renders with the Iray server solution. And we were pleasantly surprised by the Iray Plus API. It's super clean. It took us less than a week to get our first images. Integration was far from done, but in less than a week we had encouraging results, so it was nice. Here's a quick demo of where we are right now concerning the Iray Plus integration. So here's how it goes. So the way we designed it, it's actually fairly intuitive. Get your scene, that's a fairly simple scene. And you just turn on Iray. And that's progressive path tracing. So right now we're using the basic interactive mode. You have your scene, we'll switch to photoreal. Since it's relatively basic, this is using I think it's 780 card. So in real time, you can just move around. You get soft shadows. You get, all the global animation goodies of a path tracer. And everything is dynamic, so you can, within your Unity scene, just move things around. You can, change the light color. That's fairly basic. There's a lot of things we don't show in this video because, it would take so much time. But now you can move an area light in the editor, and it moves. You can, iterate on that, find the right position, bake your stuff afterwards, and then, it's done. Change your colors, no problem there, of course. It supports, we try to support every single setting from Unity and just find something that makes sense when we map it to Iray. So, get the sun back up. The entire scene is dynamic. So I think here we will duplicate this character. Come on, duplicate it. There you go. So it's fully dynamic. There's no, there was no video editing in in this video. It's just, it works. I just couldn't run it on my laptop here. It takes a better graphics card. So we exposed the depth of field effect. So it's a depth of field straight from the render itself. So it's not a post-processing effect. And then, we can delete stuff. Iray Plus comes with a fairly complex and intuitive, I think, material system. So we exposed that as well. It's different data, but we did a simple automatic translation of the Unity materials. So you can change your materials, at will. There's a library of built-in materials that come with Iray, so you can just use them. It's no big deal. You can add coatings, decals, and all that layered materials. We support animations. That was kind of the point. So you can have skin mesh renderers in there, and it will just adapt correctly. It's not shown in this video, but we can also, go in play mode, get back in edit mode, so it works in both modes. So we can have a, distributed rendering that works with the pre-built scenes and stuff like that. That's pretty much it. I think for this demo, we'll just, set the sun down. It's a nice ending right there. And yeah, so we mapped the, the skybox to something that's equivalent in Iray, and it's very pretty. So yeah, so that was our integration of Iray, real quick. Now that's a simple scene, that's a simple demo, but it doesn't really showcase everything it can do in the end. So we asked our artists to build very simple Unity scenes, very simple geometry. So what you see right now is the Unity game view, basically, that renders it's a very simple geometry, a glass, a straw, and that's it, a single light, single surface, using standard materials. So you just take this scene and put it into Iray and just render for, every scene that we show here is less than 10 minutes on, I think it was a 780 card from NVIDIA. So each of these scenes, you see nice, nice reflections, refractions, caustics, and everything just come for free. We didn't have to change any data. It just, it was translated as is. Change. All right. That's your standard color chromatic dispersion example. So that's a prism array with the integrate light at multiple wavelengths. So we get these kind of shots with very simple geometry as well. That's all in Unity, so we didn't, have to do anything fancy. Just imported the assets, move things around. Unity is a great, authoring tool, so leveraging that makes it easy. That's a subsurface scattering with candles. No big changes to the original geometry. Nothing, actually, just the materials. This is actually using the Sunshine plugin. If you guys use it, it's great. That's real time in Unity. We can replicate, give or take the same results using Iray, using, again, subsurface scattering, but applied on a bigger volume. Then we have, the diamond scene is back. That's our depth of field test, depth of field with transparent objects. With a few minutes of rendering and a few, 100 samples, it gives you this with nice caustics and everything. That's using Iray 2015.0, I think, and it's, the speed improvement from 2014 was just massive. A few challenges, it's not, it wasn't all, free for sure. Dealing with assembly reload in Unity, dealing it with executing scripts in edit mode is usually a pain. We had to deal with that, so serializing events and stuff like that was not, super fun. Not all assets are created equal in Unity. So to translate Unity assets to the Iray database, we basically need to fetch this data somehow. What do we do for particle systems, for example, for terrain, for procedural objects? But what are we doing for shaders? If you have a vertex shader that moves your vertices, that animate them with time, so what's the plan there? We're working right now on a transform feedback customization of the engine, so we need to customize Unity since we have the source. It's something we actually can do to get those transform vertices back at the end of a frame and then inject them back in Iray to get the final result. You can't share graphic resources between the two renderers. That's just how it works. That's to support distributed rendering. So let's say you have 2 gigabytes worth of texture in your VRAM. You won't be able to share that amount of data. So our trick for that is we just skip a few MIP levels when we use Unity, when we render in Unity to keep the memory footprint low in Unity, and upload the high-resolution textures in Iray, so on the local machine. It's a good trade-off. And well, last but not least, Iray is a black box. You can't, when it crashes. It's pretty complex. It's pretty deep, so we need good support. Lightworks provided us with great support for that. And we were able to quickly iron out a few issues we had during development. It's not about engineering only. It's also about content creation. This is not, the accumulation buffer technique is a push-button solution. Just, you can automate everything and it works. This, you need to customize your materials. You need to customize your lights. You need to save this data with your scene. There's a few challenges there, but it gives you much better results in the end. So we think it's worth it if you think about it up front. You need to, think about more detailed geometry since it's a global simulation. You want to avoid bump and normal maps to avoid shadowing artifacts on your geometry. Otherwise, the lighting, the shading won't match the shadows, for example. You can't kill shadows. It makes no sense for Iray to just turn off shadow casting on some objects, and every triangle has 2 faces. And some scenes with subsurface scattering, they're not simple. They will take some time, and you will lose interactivity. This solution is completely async, so you won't, choke the Unity editor completely, but your first sample in Iray will take some time to render. That's the example of the shadowing artifact we get with when you mess with geometric versus shading normals, and they don't match. So that's why you need more detailed geometry. Both Iray and Unity use completely different, well, not that different, but different material systems. Iray is based on the MDL specification, which is using a BSDF model. That's basically saying we take care of the diffuse reflection, specular refraction, but also transmission of light through volumes. So it's a really great system that actually models reality. It also has a different macro facet model. So they talked, I think, at Unite earlier about the GCX, anyhow, approximation. I think Iray is using the RNIR approximation. So you don't, all in all, it just means that you can translate Unity materials one-to-one to Iray materials out of the box. There are some limitations. You need to work with them. But you can get a pretty good rough approximation with automatic translation. It was a successful experiment, that's for sure. We really like what we see with Iray. Yet we feel still that we need this artistic control over the rendering internals that we don't get since it's a complete black box solution. So what's next? Should we invest in building our own renderer, yet another renderer? Should we use an hybrid approach? It's not clear yet, but we have a few ideas. Here's a sneak peek of something we're working on. Basically, the idea here is to use everything, reuse the shading from Unity, and just use optics, directly optics, so not Iray, just to compute shadows. So what we're doing, we use the exact same interface we use for Iray, and we ray trace soft shadows from this geometry and inject back these shadows in the rendering pipeline through screen space attenuation maps. So each light has a screen space buffer that basically represents its attenuation at this pixel. And we sample that differently by overriding the standard rendering pipelines in both forward and deferred modes. So we get that. We support, right now, at the moment, as we speak, we support spotlight, directional lights, but they're all soft. So you'll be able to see, I think, shortly. We have this radius setting. That's basically the radius of the sphere that is used, that we sample to determine if the light should be, if the shadow should be soft or hard shadows, basically. That's the only difference. We started to implement support for some material properties. So, for example, cutout geometry. The little egg shape you see at the bottom is it's an egg with some holes in the textures, and it has a cutout material. So you can see the point light inside the egg projects lights on the walls, on the geometry. The entire scene is dynamic as well. And we can move lights. Everything is dynamic. There's nothing static in this scene. You can move light around. You can move objects. It kind of works. And it's much faster to just do the shadows, obviously, than a full-blown rendering of the entire scene. And we can reuse our shaders. So that's about it about high-quality rendering. That's all offline. It's not something in real time, but we get interactive rendering. It's not final, but it's at least a good play blast and lets you work faster. So we also develop production tool to wrap it all together. The way we see animated productions in Unity is this. So every shot in a story is a scene in Unity. We're using great sequencing tools that are made available on the asset store. I'm thinking about the Cinema Director plugin from Cinema Suite. It's great. You should try it. And what we realize at Hibernum is that stakeholders that need to review this content, that need to take an action, or this part of the cinematic is not good. They're not Unity users. They don't want to get the latest version of the project. They don't want to hit render. They just want to see the content and review it and take an action on it and instruct people to change stuff. So we built two tools. We built a server-side, an internal web service. That's basically a glorified build system. That's it hooks to our version control system, gets the commits, and resolves which scene changed, and re-renders them server-side, and makes that data, the metadata, and the final frame data available through a REST API. On the client side, as a proof of concept, as a simple prototype for now, we created a Unity-based application that consumes this data and lets stakeholders that don't need to install Unity at all on their machine just scrub through the final frames, see what's going on in the timeline. So I'll give you a quick overview of this process. We don't have a whole lot of time to cover everything, so I'm just kind of running through this presentation. I realize it, but bear with me. So again, nice logo. So that's, an artist realized that this poor bird is broken. It doesn't flap. We need to fix that, obviously. And so we'll just, select the right actor and fix it. That's the Cinema Director plugin I was talking about. So automatically, now the assets are pushed, and our server-side build system basically picks it up. Automatically, there's no button to be pushed or anything. Just picks it up and realizes that need to fetch the latest assets, need to load Unity, open that scene that just changed, the bird scene, and needs to re-render it. So now you'll get a glimpse of that scene was a test for the motion blur accumulation buffer technique. So you'll see how it looks. That's on the build machine. Nobody's driving this. It's just fully automated. It renders the scene, accumulates the time, basically simulates the exposure time and accumulates the samples, writes the final frames on disk, and creates a few videos for different formats. The build is now completed, and the data is available on the server. On the client side, what we have is a simple tool. It's a standalone application. So we have this, it's for demo purposes. It's a flying bird. That bird is broken. It's very sad. But we see on the right-hand side of this little clip on the timeline that we're at version 5. And on the inspector on the left, we have all the other tests that we have in the project, and all audio clips, video clips, and stuff like that. We can preview these scenes. These frames that take a few seconds to render, you saw it on the build machine. Now they're all in video format, allowing us to scrub through them and have fancy animations. So we just updated that clip to the latest version, fixed that story, and we'll be able to save that story later. It's a simple tool. We think it's relatively powerful. There's a few features missing, but we're working on it. So we can, for example, just drag clips on the timeline, create a very simple story out of it. I don't think it's shown in this video, but you can actually export the individual HD frames of this story on your local computer and basically start a, I don't know, Premiere, Nukes, After Effects project of that for post-production. Or just synchronize frames that you add before and update your post-production product. So yeah, that video is running a little bit long, but you can do basic timeline operations, and it's been very helpful so far with our productions. So what's next? Definitely, we really want to decouple the rendering from the asset builds. We'd like to re-render the same scenes at the same version. So we'd like to record this animation format in some format, and then be able to change the render settings and produce different animations on the fly based on needs. So if you need a quick play blast or a final video, you could do that. We want to improve that little tool I showed you. Want to integrate the feedback loop I talked about, so stakeholders would actually add feedback, draw stuff on screen, figure out which artist modified that pixel last, and either directly communicate with it or create a ticket or something. Since it's a Unity-based application, we could create asset bundles from this data and have a 3D viewer per clip and move the camera, move the point of view on a per clip basis, and add rich comments to this pipeline as well. That's something we could do. Talked about the export to different post-processing packages, but also transitions between clips and some basic features for an animation tool. We also believe that this pipeline, this kind of build pipeline, is super flexible for different use cases in the game production side of the company. So we're picking right now some different tools to improve texturing, to improve modeling from this exact same pipeline. So that's it. That was fast. So in conclusion, Patrick and I, we covered 3 aspects of our animation production pipeline. How to create new content using mocap, live in Unity, so in real-time mocap streams. We're using off-the-shelf sequencing plugins for the actual sequencing within Unity scenes. That's something we haven't, put enough emphasis on. But when it comes to render these frames, we developed some offline, high-quality rendering techniques. The key advantage here is that it's based on the exact same assets that you already developed for your in-game cinematics. So you create once, and you either push a button or slightly adapt your scene to render much higher quality images based on the exact same assets. And we talked about new production tools to just put it all together and basically make sure that everyone on the production side is involved with our animation production pipeline, not just developers in Unity. So the last message, what we want to do is just stop wasting time porting assets. We don't want to duplicate work anymore. We want to stay in Unity. We think it's a very flexible authoring tool. We really like it. So we don't want to port back stuff we wrote for games back in Maya or Max or whatnot. So we want to start using Unity for animated productions. And that's it. That's all we got. So you got questions? Thanks.
I have a question.
Sure.
In your API 2 of 2 section, you mentioned perception neuron as what's next.
Yeah.
How do you implement tools such as that into the real-time mocap scenario for what you're talking about with output with iRay?
Yeah, we can directly use the API we developed. We can do DLL with perception neuron, so we can use their SDK to really get the motion capture data and to retarget that directly in Unity to the bones of the actor.
Do you see that affecting the speed of your production overall?
Yeah, because we can very see what we will have in the game very early in the pipeline, so it's very easier to get what we will feel in the game.
Do you see the overall output with Imagery as a better quality output?
For animation, I mean, you saw we support like a skin mesh renderer, but that same renderer can be driven by a mocap stream. So yeah, the actor could see its ray trace version with a very high-end rig. So we're talking 4 GPUs or maybe a VCA that could connect to this and get really, really nice results. There's a few demos of this kind of concept online. That's something we could do definitely. It would already be working as far as we know.
Awesome, thanks.
You. Yes.
I was wondering if you guys were looking into possibly incorporating rendering out separate passes for post-production and something like Nuke or After Effects.
Yeah, we actually add that. We didn't include it in the presentation because time's a factor, but we could have since there's still 14 minutes left. But that's something we do. With Imagery right now, we support all the standard outputs from renderers you're used to in Max and Maya. That's already supported. We also support the light path expressions. So that's something that they added relatively recently that lets you modify lighting settings. That's weird. That's weird. So yeah, yes, we do support multiple passes. We also support the exact same concept. We kind of have a standardized rendering pipeline. So either you saw it's literally a drop-down box that selects the renderer. So if you use Unity or Imagery or our own custom shadow renderer, they all support multiple passes. So you can have an object ID pass, you can have just the diffuse channel, just the whatever, and it works.
Thank you.
No problem.
Any other questions?
All right.
That's it.
That's pretty much it. Thanks.
Thanks.